Hi, today's video is going to focus on some of the techniques, shortcuts for taking derivatives without having to use first principles. Turns out that some functions are complicated so complicated that even using shortcuts still makes a lot of hard work for algebra skills anyway. So what we need to do before we take the derivative of any function is we need to make sure we understand the nature of the function, what's there. Here we see the sum of really what amounts to four unique functions. This is a constant. This is a 3 over x squared function. This is a 3 over square root of x function. And here's a 4x squared. So if we add them all together, lucky enough, we know that the derivative of the sum of functions is equal to the sum of the derivatives. So here, if you have two functions and you want to take their derivative, you just take the derivative of both functions separately and add them together. Second thing I need to be aware of is I need all of this stuff to be in a form that I could use power rule on. The trickiest part for most people is this square root of 5. Some people will differentiate the square root of 5, but remember we're differentiating with respect to x. X is the variable here. So the implied variable is x to the 0 power, because x to the 0 power is 1. So we have 1 times the square root of 5. Now if we apply the power rule here, we're going to have 0 times the square root of 5, which is 0, x to the negative 1, or just 0. More important way to look at this is a constant. If you take the derivative of a constant, you should always get 0 because y equals square root of 5 represents a horizontal line. The slope of a horizontal line is always going to be 0 no matter how high or low the horizontal line is. Anyway, now that I apply the power rule, 4 times 2, drop the power by 1. 3 times negative 1/2, drop the power by 1. 3 times negative 2, drop the power by 1. Be careful, negative 2 minus 1 is negative 3. And then we add 0. So all we have to do now is just clean everything up, get rid of the negative exponents, and put it back into radical form. So negative 3 as an exponent means divide by x cubed, and 3/2, we could look at x cubed square root, and the negative, of course, means it's in the denominator. So make sure you have those skills. The other thing, it was a little reminder that 2 times the square root of x cubed is the same as 2x times the square root of x. That's an Algebra 2 review. If you don't know why that is, please feel free to ask. In the second function that we're looking at, my first reflex might be to use the quotient rule here, and the quotient rule is used whenever you see a function divided by a function. However, this is a constant function, and constant functions behave in a much more well-behaved manner. So whenever we see a constant in the numerator, I would avoid using the chain rule. I'm sorry, the quotient rule. So what I am going to do, though, is I'm going to take this denominator and bring it up to the numerator with a negative 1 exponent on it. Now all I have to be in charge of is making sure I know how to use the chain rule properly. Anytime we have a composite function, that's one function inside another function, we have to remember the chain rule. And there's reasons for this, and I try to talk about it in class, but for some it's hard to process. So just remember that here we have x minus x cubed, which is a function in and of itself, and then we have to the negative 1 power, which is a reciprocal function. So this is an example of a composite. So I'm going to start by taking the derivative of the outer function. Notice all I did was multiply the negative 1 times the 2, and then drop the power by 1. And in order to keep the rate of change correct, we have to also find the rate of change function for the inner, which is x minus x cubed. So I take the derivative of that. Here, all I did was take the negative 2 power and bring it down to the denominator, make a positive power. So x minus x cubed squared is in the denominator, and the derivative of x is 1, and the derivative of x cubed is negative 3x squared. And so all I'm going to do now is distribute the negative 2 into the 1 minus 3x squared, and I get that. Looks real nice. Now some students may not have done the chain rule here. They might have looked at this and tried using the quotient rule. It's not wrong. You'll see what I'm doing here is applying the quotient rule, which is the ho d high minus high d ho over ho ho. And so we have the x minus x cubed times the derivative of 2. Well, the derivative of 2 is 0. Then we have 2 times the derivative of this stuff, which is 1 minus 3x squared over x minus x cubed squared. So all this 0 stuff over here makes it useless. I distribute the negative 2, and I get the exact same function that I had before. You can see using the quotient rule is not wrong. In fact, it's not that much harder, but you can see it takes a little bit more effort to keep everything straight than if you just clean it up at the beginning and then use the chain rule instead. Here, a situation arises where I would have to do two things. Either take the product rule, because this 3x is being multiplied by 2x plus 4 cubed. So here's a variable expression times a variable expression, product rule candidate. If I want to avoid that, I'm going to have to cube 2x plus 4. 2x plus 4 times 2x plus 4 times 2x plus 4, and multiply all that by 3x, and then take the power rule. I wouldn't be saving any time by doing that. So I might as well learn the product rule. Recall the product rule says if you take the derivative of two functions multiplied together, it's not as easy as just taking the derivative of both of them separately. We have to take the first times the derivative of the second, and the second times the derivative of the first. I always mix the order up because it doesn't really matter. We're adding here anyway. So just take one times the derivative of another times the derivative of one. And so in this case, we have f of x is 3x and 2x plus 4 cubed. So I'm going to take the derivative of 3x times 2x plus 4 cubed, and then I'm going to take 3x times the derivative of 2x plus 4 cubed. So here again we can see derivative of 1 times the other times the derivative of 1. The derivative of 3x is just 3, so I put the 3 down. We've got the 2x plus 4 cubed untouched. We have 3x, which is right here. And then I'm going to do the chain rule. So here I have to remember the chain rule. So I've got to bring down the 3, drop the power by 1, and take the derivative of the inside stuff. So here I keep everything from above. 3x times 3 is 9x. 2x plus 4 squared just carries down. And the derivative of 2x plus 4 is 2. So that's where the extra 2 comes from. Bada bing, bada boom. 9 times 2 is 18. And now I have to remember that if I want to clean this up in a nice way, I could factor out the expression with the lowest power. So here's 2x plus 4 to the third power, here's 2x plus 4 to the second power. I'm going to take out 2x plus 4 to the second power. Also, 3 and 18 share a common factor of 3. So I take out a 3, take out a 2x plus 4 to the fourth power, 2 of those, which leaves me 1 left over. And in the second case, I already took out both of these. I took out one of the 3's, so I'm just going to have 6x left over. Oops, that jumped ahead real fast. And it cleans up real nice. I just took out 4 from here to make that 2x plus 1. I multiplied that extra 4 by the 3. So that's just for cosmetic sake. It just looks nicer. The alternative you can see here would be to FOIL out 2x plus 4 cubed. So I did that here, and it was a mess. And after I FOIL that out, then I have to multiply or distribute a 24x to get all that, and I get this gigantic polynomial with large coefficients. But the good news is, after all of that extra work, I was able to then easily take the power rule and get the derivative of this polynomial. However, to see that the two are actually the same is a little bit harder. What I did is I went and took my answer over here and FOILed it all out, and I got the same result. So hopefully you could recognize that this sort of looks like it took less work, but this is still a much better approach for finding the derivative. Alright, now we finally got a quotient, and so we apply the quotient rule, ho-de-hi minus hi-de-ho over ho-ho, and there's the hi, there's the ho, so I color-coded them, so we have ho, d-hi minus hi, d-ho over ho-ho, and the derivative of 2x minus 3 is 2, the derivative of 4x squared is 2x, and then everything I did up to this point, you can pause the screen if you want. I just multiplied negative 2x times 2x minus 3, so I got negative 4x squared plus 6x. So that's what all this stuff was down here. I distributed the 2 over here. Now I'm just going to collect like terms and get all my points. Now, alternatively, some people think they like to avoid the chain rule, or sorry, the quotient rule, because they just don't like it. It's too complicated. So the alternative, what they'll always do, is just turn it into a product rule by bringing the denominator up to the numerator with a negative exponent. So you see here, I'm applying now the product rule instead of the quotient rule, and I'll save you all the pain and suffering and just jump to the end. After I use the product rule, I have to clean it up so that it looks nice and I can work with it. So I look for common factors. I have to take out the common factors, do all this stuff, blah, 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 yada, 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 just to get to the same result that I had over here. So it might feel at first like it's an easier process using the product rule. In the long run, you're doing way more algebra to simplify than if you just go to the quotient rule, which always comes out pre-simplified. Alright, finally, real quick, this particular function, most people, when they differentiate it, are going to go straight up into the quotient rule, ho-de-hi minus hi-de-ho over ho-ho, and I'll show you all the work and the processes. Feel free to pause the screen at any time to see what I did. What I'm doing here, again, is not wrong. It's just really tedious, and it's very highly probable that I'm going to make an error somewhere. Once I got down to the end here, I just had 2 over x to the 3/2 power. I just make that -2 over the square root of x cubed, and this is an alternative because x cubed square rooted is x times the square root of x. So these are all synonymous forms. Instead, what if I looked at the function and decided to distribute the x to the 1/2 on the bottom so that I just get that? And this is a much easier function to differentiate because it's just a polynomial, and there it is. That's the derivative. So the lesson here for all of these functions is that you should make sure that you think about the function that you're differentiating, look at it, understand its nature, and by understanding the nature of the function, it'll help you choose the best approach for finding the derivative. So it's not always going to be obvious, do this or do that. Sometimes you might have to do some adjusting or finagling to the function to make it easier to differentiate. That's a good skill to pick up. Again, if you don't walk out of the class with anything, you should at least be able to think and problem solve and reason mathematically before it's all said and done. The video is getting really long, so I just wanted to just kind of quick brush over this last one. This is determining who understands the chain rule versus who just knows how to use it. So the derivative here, chain rule, is the derivative of the outside, or sorry, times the derivative of the inside, which cleans up here. So to find g prime of 1, I find f prime of 1 over 2 times the square root of f of 1. Up here it says f prime of 1 is 3, so I replace it. F of 1 is 4, so I replace it. And square root of 4 times 2 is 4, so this is g prime of 1. Please pause the screen and look at this because this is going to be on the test, and there's going to be one just like it. So make sure you understand what this is all about. Thank you for watching. Have a good day.